So lesson 7 is all about dynamics and friction. So how are these forces acting with friction? We learned last time that friction is the force that opposes motion and it is always parallel to the surface. Let's go a little bit more in depth into that. Like I said, friction is a force opposed to motion, always parallel to the surface. We're going to talk first about static friction. Static friction is what keeps an object in place. All right, it's still parallel to the surface in the direction required to prevent motion. So if I'm pushing to the right, the friction is working towards the left. If I'm pushing to the left, friction's then obviously towards the right. Static friction can be any number of values because static friction is only going to work as hard as it needs to work in order to keep an object in place. So if I only put 1 Newton of force on an object, static friction only needs to put 1 Newton of force to fight me. The next thing we're going to look at is the fact that friction is proportional to the normal force. Remember, the normal force is that force that helps support an object on a solid surface. We see our formula for static friction here. Right. You may see this in a couple different ways. Another way that we see this is this little curly f with the subscript s is less than or equal to our mu, the Greek letter mu, sub s times our normal force. And I do want to reiterate the fact that normal force can have a couple different notations. The last bit is that mu sub s is our coefficient of static friction. This is a property of the materials that are rubbing together, so it will change from situation to situation. You will be given this kind of information in a problem or enough information to solve for that value. This is one of your few values that is allowed to be unitless. All right, so that's what you're looking at here. So we're going to go ahead and do an example with this particular concept in our brains. We have a 0.54 kilogram book sitting on the surface of our desk. We're going to push on our book with a force meter, increasing our force slowly. As we increase this force, we see the book then begin to slide. Just before our book slides, we see our force meter reading 4.1 newtons. We're going to use this information to find what is the coefficient of static friction. We should be going ahead and drawing force diagrams at this point. So we're going to start this particular problem by doing so. So I have my book. All right. I have my point from which all my forces act from. I have my normal force, which is up, since it is on a surface. I have my weight due to gravity down. I have the push that I am putting on it. I'm just going to use P for push here. And then, of course, we have our frictional force acting on our object. We do see the fact that it is static friction, it is completely still, so in all cases, not only the up and down, but the across, our acceleration is equal to 0. Okay, this is very important, as you know, as we are building our equations for this particular situation. So we're going to look at the sum of the forces first in the y direction is equal to the mass times our acceleration in the y direction. As we already established the fact that our acceleration is equal to 0, my right-hand side then goes to 0. Right? We are then looking at what are the sum of our forces in the y direction. We do have the normal force, which is up, making that quantity positive. And we have our weight down, which is making that quantity negative. Because it is equal to 0 and there are no other forces present in the y direction, we do see the fact that our normal force is equal in this particular case to our weight. So that goes ahead and takes care of what's going on in the y direction for now. we can go ahead and move on to what's going on in the x direction, since that's the more interesting bit of information. So we have the sum of our forces in the x direction is equal to our mass times our acceleration in the x direction. We already established the fact that this is static friction. Our book is not moving, so our acceleration in the x direction is therefore 0. Our sum of our forces in the x direction are our push, which I went ahead and set as positive, minus our frictional force, which is to the left, which is negative. That goes ahead and tells us that our frictional force is equal to our push. All right, and we can continue to move on. We established as a part of our formulas that static friction is equal to mu sub s times our normal force. So we can continue writing the fact that our push is then equal to mu sub s times, our normal force. We established as a part of what was going on in the y direction that our normal force was equal to our weight, which is mg. So we see that our force of our push is equal to our mu sub s times mg. We are solving in this particular case for the coefficient of static friction, so we can do some algebra from here. Alright, so this is our equation, solve for everything, solve for the variable that we want. So now it is a matter of plugging and chugging. We see that our force meter read 4.1 newtons, so that's the quantity that's going to go in for our F of P. We see the fact that our mass is equal to 0.54 kilograms of our book, and we are going to assume that our book is on Earth. When we make that assumption and plug all of our numbers in, we do finally get the fact that our coefficient of static friction is equal to 0.77. Right? And there are no units that go with our coefficient of friction. It is just a unitless number. Right? That goes ahead and takes care of part A on this particular example problem. For part B, this goes back a little bit more towards the definition of what's going on with static friction. Remember, static friction can take any range of values from 0 all the way up to that maximum value. We found the maximum value of our static friction with the 4.1 newtons. All right. So then, if you push on the book with a force of 2.5 newtons, which is less than 4.1, what is the magnitude and direction of the static friction? Well, the magnitude is going to be 2.5 newtons, and the direction is going to be opposite the push. Just remember that static friction is only going to work as hard as it needs to. Nature is very lazy. It doesn't want to do more than it has to. So it can only be the 2.5, and it does oppose the motion. It's going to be opposite that. So that does bring us to our next idea of friction. Our next idea is kinetic friction. This is what happens when we have two objects sliding past each other. Kinetic does mean movement, so we are looking at the fact that this is the friction we have when there is movement. Like the static friction, it is always parallel to the surface, and it is always opposing the velocity. So if my object is moving to the right, my friction is moving to the left. Right? It is proportional to the normal force, but unlike static friction, our kinetic friction only has one set value. Do notice the fact that that is an equal sign in this particular case. Like our static friction, we do have a couple little bits of notation. Right? So we can see the curly F of K is equal to our mu of K times our normal force. Right? And the coefficient of kinetic friction, again, unitless, and a property of the two materials will change depending on the materials you're looking at. So we can go ahead and look at an example problem for this particular case. We are going to look at the magnitude and direction of the kinetic friction if you push the book with a force of 3.2 newtons. So we are going to do as we've started all of our other problems and start by drawing a force diagram. I'm going to draw it up here at the top since I'm going to use it for all 3 problems. So I have my object. It has a weight. It has a normal force. It has the force of push. And it has the kinetic friction. I do want to go ahead and add to this particular problem the fact that we do have a velocity and it is moving to the right. We're going to go ahead and it's in the positive direction. But I also want to note the fact that it is being pushed at a constant speed. If you have a constant speed, we know that our acceleration is equal to 0 again. Right? So we want to know the magnitude and direction of the kinetic friction if you push the book with this particular force. So the sum of our forces in the x direction is equal to the mass times the acceleration in the x direction. We already established no acceleration, so this term is equal to 0. As a result, our x direction, we have the force of the push minus our kinetic friction is equal to 0. So our kinetic friction is equal to the push, which we established was 3.2 newtons. And that's already our answer for part A. All right. For the next part, we are going to look at the normal force. The normal force is dealing with what's going on in the y direction, as we remember for this particular situation. So our sum of our forces in the y direction is equal to the mass times our acceleration in the y direction. Remember, no acceleration, this term goes to 0. We have our normal force minus our weight is equal to the 0. So our normal force is equal to our weight, which is mg. Our book from before was 0.54 kilograms times our value for gravity does give us a normal force of 5.29 newtons. All right, so we've now established the answer for part B. So from here we have our value of our kinetic friction, we have the value of our normal force. We can go ahead and find the, we can go ahead and find the value of our kinetic friction. So kinetic friction is equal to mu k times our normal force. Therefore, mu k is equal to our kinetic friction divided by our normal force. That means we have part A divided by part B. So 3.2 newtons divided by 5.29 newtons gives me a coefficient of kinetic friction of 0.60. Remember, no units. The coefficients have no units. All right. Static and kinetic are the big frictions that we will deal with. Rolling friction is another one. It is parallel to the surface and opposite to the direction of the rolls. So if our wheel is rolling forward, our friction will be moving backwards. Still proportional to our normal force. And we do have another coefficient of friction in this case. It is the coefficient of rolling friction. It is very small. This rolling friction is very small compared to all of the